Welcome to the fascinating world of satellite remote sensing. In this video, we'll explore how scientists use satellites to observe and understand our planet from above. Whether it's monitoring air quality, tracking wildfires, or studying the atmosphere, remote sensing provides critical insights without ever touching the ground. By the end of this journey, you'll know what the electromagnetic spectrum is, how satellites detect radiation, and the different types of satellite resolution. Let's embark on this exploration of technology and science that helps us see the Earth in new ways. Remote sensing is all about collecting information from a distance, without making direct contact with the object of interest. Imagine being able to study forests, oceans, or even city landscapes without ever setting foot there. That's the power of remote sensing. Satellites orbit high above, capturing data about the Earth's surface and atmosphere, which is then analyzed to reveal patterns and changes. This technology is essential for environmental monitoring, disaster response, and scientific research. It's like having a global eye in the sky, always watching and learning. Remote sensing isn't just about taking pretty pictures from space. It's a vital tool for a wide range of applications. Scientists use it to monitor air quality, track the spread of wildfires, and study dust storms. Governments rely on satellite data for urban planning and disaster management. Even farmers benefit using remote sensing to assess crop health and manage resources more efficiently. The possibilities are nearly endless, making remote sensing an indispensable part of modern science and daily life. Choice of remote sensing platform depends on what information is needed. Do you want detailed images or broad coverage? How often do you need updates? Satellites, airplanes, and even drones can serve as platforms, each with unique strengths. For example, satellites are perfect for global long-term monitoring, while drones can capture high-resolution images of specific areas. The end application guides the selection, ensuring the data collected is fit for purpose. Let's take a closer look at some remote sensing platforms in action. Satellites orbiting the Earth capture images and data across vast regions, while aircraft can be deployed for more targeted missions. Each platform is equipped with specialized sensors designed to collect the most relevant information for the task at hand. The choice of platform impacts the detail, frequency, and type of data collected, making it a crucial decision in any remote sensing project. Remote sensing allows us to observe our planet in ways that were once unimaginable. From tracking the movement of clouds to monitoring changes in land use, satellites provide a comprehensive view of Earth's dynamic systems. This bird's-eye perspective is invaluable for understanding environmental changes, predicting weather patterns, and managing natural resources. With each new advancement in technology, our ability to monitor and protect the planet grows stronger. The heart of remote sensing is electromagnetic radiation. The Earth, ocean, land, and atmosphere all interact with solar radiation in unique ways. Some of this energy is reflected back into space, while some is absorbed and remitted as infrared or microwave radiation. By measuring these different types of radiation, satellites can reveal a wealth of information about the planet's surface and atmosphere. Understanding these interactions is key to interpreting satellite data accurately. Satellites are equipped to measure a wide variety of features on Earth. They can detect the atmosphere, trees, water bodies, grasslands, bare soil, pavement, and built-up areas. Each of these surfaces interacts with radiation differently, allowing satellites to distinguish between them. This capability is crucial for mapping land cover, monitoring environmental changes, and supporting disaster response efforts. The data collected forms the foundation for countless scientific studies and practical applications. The intensity of radiation measured by satellites is influenced by both surface and atmospheric conditions. Clouds and aerosols can reflect, absorb, or emit radiation, altering the signals that reach the satellite sensors. By analyzing these interactions, scientists can infer valuable information about the Earth's surface and the composition of the atmosphere. This process is essential for understanding climate dynamics, weather forecasting, and environmental monitoring. Remote sensing involves a series of steps, starting with the collection of geophysical information and the application of radiative transfer theory. Satellite sensors measure parameters like spectral radiance, which are then processed using retrieval algorithms. The final data products are used in a variety of applications, from environmental monitoring to resource management. Each step in the process is carefully designed to ensure the accuracy and reliability of the information gathered. Satellites are equipped with a variety of sensors, each designed for specific observation tasks. The combination of satellite platform and sensor determines the type of data collected. For example, the Aqua satellite carries instruments that monitor water vapor, clouds, and atmospheric gases. The choice of orbit, whether polar or geostationary, also affects the coverage and frequency of observations. Understanding these components is essential for interpreting satellite data correctly. Discussing satellite remote sensing, it's important to distinguish between the satellite itself and the sensors it carries. The satellite acts as the platform, orbiting the Earth and providing a stable base for the instruments. The sensors, on the other hand, are the devices that actually collect the data, measuring everything from temperature to atmospheric composition. This distinction helps clarify how different missions are designed and what kinds of data are available. Satellites and their sensors can be characterized in several ways. Orbits can be polar or geostationary, each offering different coverage patterns. Energy sources may be passive, relying on sunlight, or active, emitting their own signals. Measurement techniques vary, including scanning and non-scanning methods. Finally, the resolution, spatial, temporal, spectral, and radiometric, determines the detail and quality of the data collected. Each characteristic plays a role in how the satellite system is used. There are two main types of satellite orbits, polar and geostationary. Polar orbits pass over the Earth's poles, allowing the satellite to scan the entire planet as the Earth rotates. Geostationary orbits, on the other hand, keep the satellite fixed above a single point on the equator, providing continuous coverage of the same region. Each orbit type has its advantages, depending on the observation needs and the area of interest. Aqua satellite is a prime example of a polar orbiting satellite. It circles the Earth, collecting data on water vapor, clouds, and other atmospheric properties. Its orbit allows it to scan the entire globe, providing valuable information for climate research and weather forecasting. The data from Aqua and similar satellites help scientists understand global patterns and trends, supporting efforts to protect the environment and respond to natural disasters. How often a satellite observes the same area depends on its orbit. Polar orbiting satellites like Aqua and Terra typically provide 1-3 observations per day, while geostationary satellites can deliver updates as frequently as every 30 seconds. This difference in observation frequency is crucial for applications like weather monitoring, where timely data is essential. Future satellites promise even higher observation rates, further enhancing our ability to monitor the planet in real time. Area a satellite can observe in a single pass is called its swath width. Some satellites like MODIS have a swath width of over 2,000 kilometers, allowing them to cover the entire globe in just a few days. Others, like CLAPSO, focus on much narrower areas for detailed observations. The choice of swath width affects how quickly and how often data can be collected, making it a key factor in satellite mission design. Different satellites offer varying coverage capabilities. MODIS and VIRS provide broad, frequent coverage, making them ideal for global monitoring. MISR and CLAPSO, on the other hand, focus on more specific regions or phenomena. By combining data from multiple satellites, scientists can achieve a comprehensive understanding of Earth systems, balancing detail with coverage and frequency. Satellite sensors can be classified as active or passive. Passive sensors detect natural energy that is emitted or reflected by objects, such as sunlight reflected from the Earth's surface. Active sensors like radar and LiDAR emit their own signals and measure what is reflected back. Each type has its advantages. Passive sensors are great for broad, continuous monitoring, while active sensors excel at capturing detailed information in specific conditions. Some well-known satellite sensors include MODIS, MISR, OMI, and VIRS. MODIS and VIRS are passive sensors, capturing reflected sunlight and emitted thermal energy. CLAPSO, on the other hand, is an active sensor using LiDAR to probe clouds and aerosols. Each sensor is tailored to specific observation needs, contributing unique data to our understanding of the planet. Resolution is a key concept in remote sensing, determining the level of detail in the data. There are 4 main types: spatial, temporal, spectral, and radiometric. Spatial resolution refers to the smallest object that can be detected. Temporal resolution is how often data is collected. Spectral resolution describes the sensor's ability to distinguish between different wavelengths. Radiometric resolution measures the sensor's sensitivity to differences in energy. Each type of resolution plays a vital role in the quality and usefulness of satellite data. Let's break down the 4 types of resolution in remote sensing. Spatial resolution is about how small an object can be and still be detected. Temporal resolution is about how frequently the same area is observed. Spectral resolution refers to the number of wavelength bands the sensor can distinguish. Radiometric resolution is about how finely a sensor can measure differences in energy. Each resolution type is determined by the satellite's orbit and sensor design, and different sensors have different strengths. Digital image from a satellite is made up of tiny units called pixels. Each pixel represents a specific area on the Earth's surface and has its own intensity value and location. The size of a pixel determines the spatial resolution of the image. The smaller the pixel, the higher the resolution. Understanding pixels is fundamental to interpreting satellite images and extracting meaningful information from them. Spatial resolution is crucial because it determines how much detail can be seen in a satellite image. For example, MODIS provides resolutions from 250 meters to 1 kilometer, while VIRS offers 375 meters. Higher spatial resolution allows for more detailed mapping and analysis, making it easier to identify features like roads, buildings, and small bodies of water. The choice of spatial resolution depends on the application and the level of detail required. Spectral resolution describes a sensor's ability to distinguish between different wavelengths of light. The finer the spectral resolution, the more precisely the sensor can identify specific materials or features. Multispectral sensors like MODIS capture data in several broad bands, while hyperspectral sensors like OMI and AIRS can detect hundreds of narrow bands. This capability is essential for applications like vegetation analysis, mineral mapping, and water quality assessment. How does spectral resolution matter? Different surfaces like pinewoods, grasslands, and water reflect light in unique ways across the spectrum. By measuring these differences, satellites can distinguish between various land cover types and monitor changes over time. High spectral resolution enables more accurate classification and analysis, supporting a wide range of scientific and practical applications. Radiometric resolution refers to a sensor's ability to detect slight differences in energy or brightness levels in an image. The higher the radiometric resolution, the more shades of gray or color the sensor can distinguish. This is expressed in bits. An 8-bit sensor can record 256 levels, while a 12-bit sensor can record over 4,000. High radiometric resolution is essential for detecting subtle changes and producing sharp, detailed images. The more sensitive a sensor is, the higher its radiometric resolution. This means it can detect finer differences in brightness, leading to clearer and more precise images. For example, NASA's MODIS sensor has a 12-bit resolution, allowing it to distinguish over 4,000 brightness levels. This capability is especially important for applications like land cover classification, where subtle differences can be significant. Radiometric resolution can be visualized as the number of shades or levels in an image. A sensor with only 2 levels can only distinguish between black and white, while one with 16 levels can show a range of grays. The higher the number of levels, the more detailed and nuanced the image becomes. This is crucial for accurately classifying different land cover types and detecting subtle changes in the environment. Temporal resolution refers to how often a satellite can observe the same area. This is largely determined by the satellite swath width. The wider the swath, the more frequently an area can be revisited. For example, MODIS and VIRS can achieve global coverage in 1-2 days, while geostationary satellites can provide updates every 30 seconds to an hour. High temporal resolution is essential for monitoring rapidly changing phenomena like weather and natural disasters. One of the biggest challenges in remote sensing is balancing the different types of resolution. It's very difficult to achieve extremely high spatial, spectral, temporal, and radiometric resolutions all at once. Improving one type of resolution often means compromising another. Scientists and engineers carefully design satellite missions to find the best balance for their specific goals, ensuring the data collected is both useful and practical. Let's recap what we've learned. Remote sensing uses satellites to collect information about the Earth without direct contact. The technology relies on understanding electromagnetic radiation and how it interacts with the planet's surface and atmosphere. Satellites come in different orbits and carry various sensors, each with unique strengths. The four main types of resolution, spatial, temporal, spectral, and radiometric, determine the quality and usefulness of the data. Balancing these factors is key to successful remote sensing. Satellite remote sensing has a profound impact on our daily lives. From predicting the weather to managing natural disasters, the data collected by satellites supports countless decisions and policies. Farmers use satellite imagery to optimize crop yields, while environmental agencies monitor deforestation and pollution. The technology continues to evolve, offering new tools and insights for a sustainable future. The future of remote sensing is bright, with new satellites and sensors being launched every year. Advances in technology are enabling higher resolutions, faster data delivery, and more sophisticated analysis techniques. As our understanding of the Earth grows, so does our ability to protect and manage its resources. Remote sensing will continue to play a vital role in addressing global challenges and supporting scientific discovery. Accessing satellite data has never been easier. Many organizations, including NASA, provide free and open access to a wealth of remote sensing data. Online platforms and tools make it simple to search, visualize, and download imagery for a wide range of applications. Whether you're a scientist, student, or enthusiast, there are resources available to help you explore the world from above. Remote sensing offers exciting career opportunities for those interested in science, technology, and the environment. Professionals in this field work on satellite design, data analysis, environmental monitoring, and more. With the growing importance of Earth observation, demand for skilled remote sensing experts is on the rise. If you're passionate about making a difference, this could be the field for you. There are many educational resources available for learning about remote sensing. NASA's Applied Remote Sensing Training Program offers courses and materials for all levels. Universities and online platforms provide lectures, tutorials, and hands-on exercises. Whether you're just starting out or looking to deepen your knowledge, there's a wealth of information to help you succeed. Despite its many benefits, remote sensing faces several challenges. Achieving high resolution in all aspects is difficult, and data processing can be complex. Cloud cover and atmospheric conditions can interfere with observations. However, ongoing research and technological advances are helping to overcome these obstacles, making remote sensing more reliable and accessible than ever before. Remote sensing plays a crucial role in studying and addressing climate change. Satellites monitor greenhouse gases, track deforestation, and measure changes in ice cover and sea level. This data is essential for understanding the impacts of climate change and developing strategies to mitigate its effects. As the climate crisis intensifies, remote sensing will remain at the forefront of global efforts to protect the planet. Disasters strike, remote sensing provides critical information for emergency response. Satellites can quickly assess damage from hurricanes, earthquakes, and wildfires, helping authorities allocate resources and plan recovery efforts. Real-time data enables faster, more effective responses, saving lives and reducing losses. Remote sensing is an indispensable tool in disaster management and humanitarian aid. Farmers and agricultural experts use remote sensing to monitor crop health, manage irrigation, and optimize yields. Satellite imagery reveals patterns of growth, identifies areas of stress, and helps predict harvest outcomes. This technology supports sustainable farming practices, ensuring food security and efficient resource use. As agriculture faces new challenges, remote sensing will continue to play a vital role. Cities are constantly changing, and remote sensing helps urban planners keep up. Satellite data is used to map land use, monitor infrastructure, and plan for growth. By analyzing patterns of development, planners can make informed decisions about transportation, housing, and public services. Remote sensing supports smarter, more sustainable cities for the future. Remote sensing is a powerful tool for monitoring the environment. Satellites track changes in forests, wetlands, and oceans, providing early warning of problems like deforestation, pollution, and habitat loss. This information is vital for conservation efforts and environmental policy. By keeping a close eye on the planet, remote sensing helps protect natural resources for future generations. Innovation is driving remote sensing forward. New sensors, advanced algorithms, and improved data processing techniques are expanding what's possible. Artificial intelligence and machine learning are being used to analyze vast amounts of satellite data, uncovering patterns and insights that were previously hidden. As technology continues to evolve, remote sensing will become even more powerful and accessible. Satellite remote sensing gives us a unique perspective on our planet, revealing patterns and changes that are invisible from the ground. By harnessing the power of technology, we can better understand, manage, and protect the Earth. As we look to the future, remote sensing will continue to be an essential tool for science, policy, and everyday life. Thank you for joining us on this journey through the fundamentals of satellite remote sensing.